Hi folks, today we're going to be talking about what it means to be a cycle decomposition in S sub n. And so just a little refresher, permutation is just a bijection from the set of elements 1 to n to another set of elements 1 to n. It actually doesn't have to be 1 to n, but if you have n symbols, that's the simplest format for us. And we're going to denote the set of all permutations from 1 to n to 1 to n by S sub n. And what we have is this is actually given a notation called a symmetric group. When we take S sub n, so our symmetric group is just essentially our S sub n along with function composition. Okay, so we have the group going on there, and let's get used to the elements real quick and a nice notation for that. So we'll take a look at let's do S sub 6. So we have 6 elements here, and we have another 6 elements here. And we want to create some sort of function. Let's call this function sigma. Okay, and in this function sigma, we'll send 1 to 2, 2 goes to 4, 4 goes to 1. Remember, it has to be bijection, so everything kind of goes to one element. 1 to 1 and on to is what we're looking for. And we'll send 5 to 6 and 6 to 5. Okay, we have a shorthand notation for this, and rather than draw out all these arrows, what we actually can do is just take, well, we start with our 1, and where does 1 go to? Well, 1, if you look at our map, it goes to 2, and so we'll write down 2, and then we look at 2 and we see where 2 goes to. Well, 2 goes to 4, and so we put down 4 there, and now we got to see where 4 goes to. Well, notice 4 goes back to 1, and since 4 goes right back to 1 and 1 already appears there, we actually just close this off. Okay, so now moving forward, we have 3, and where does 3 go to? Well, 3 kind of loops back to itself, and so we're going to close off that with a cycle there. And then notice we've accounted for 1, 2, 3, and 4. We have 5 now. Will be our next number that we're dealing with. So 5, if you notice, it goes to 6. And so where does 6 go to in our map? 6 goes back to 5. And so since we go back to our beginning term, we close it off like that. Now, we just started at 1 and 3 and 5. We didn't necessarily have to, so sigma could be written this way, but we also could write sigma as 4, 1, 2, 3, and 6, 5. All of those mean the same thing, essentially, because notice we still have 4 going to 1, we have 1 going to 2, and now we have 2 going to 4, just in a different order with our cycle here. And the same thing with the 6 going to 5 and 5 going to 6. We get that same cycle, just written slightly differently. Usually what happens, our common notation, we start with the smallest term. So what we do on top of that, one other shorthand, so we'll go back to the 1, 2, 4 beginning. If you do have something that maps to itself, as in the case 3 here, we often just omit that. So you might see this particular cycle decomposition written like 1, 2, 4, and 5, 6. And so we can also look at maybe another one, and we'll do tau in the same set. And we have 1, 2, 3, 4, 5, and 6. So we can go 1 goes to 3, 2 goes to 1, 3 goes down to 6, 5 goes to 4, 4 goes to 2, and 6 goes to 5. So now notice for tau here, once again we can begin at 1 and see what happens. So we go from 1. Where does 1 go in our map? It goes to 3. Where does 3 go? 3 goes down to 6. Where does 6 go? 6 goes to 5. Where does 5 go? 5 goes to 4. And where does 4 go? 4 go to 2. And where does 2 go? 2 loops back around to 1, which was our first term. So we could just close that off as one cycle. So these are a couple different ways to write this. Now, if we wanted to figure out this composition, so say we did sigma composed with tau. Well, notice that equals, we have, we'll write the shorthand notation, 1, 2, 4, 5, and 6. And then composed with tau, so we're going to start with tau. That's 1, 3, 6, 5, 4, 2. So what actually happens? Well, with tau being right here, remember your function composition, you always begin with that interior function, which is essentially what tau is here. So we can start with 1 and see where 1 goes to. Well, 1 goes to 3, but then where does 3 go to? Well, if you notice back in our original equation here, we have 3 going to itself. So 1 just goes to 3. Now moving on to the next bit, where does 3 go? Well, 3 goes to 6, and where does 6 go? 6 goes to 5. So 3, when you do this function composition, will go to 5. Now we have to see where 5 goes to. Well, our 5 in tau goes to 4. And where does 4 go to? Well, 4 goes right back to 1. Leaving us with 1, 3, 5 as one of our cycles. So now we'll look for the smallest number that's omitted, and we can start with 2. Where does 2 go to? Well, 2, it goes to 1, and we'll write it down this way. So 2 goes to 1, and where does 1 go to? Well, 1 goes right back to 2. So 2 goes to itself here. 2 is fixed. Same old function composition. So we got 1, 2, 3. Now we need to look at 4. Where's 4 going to? Well, 4 goes to 2 here, and if you notice, 2 goes back to 4, so 4 is fixed. Last but not least, notice we need to check 6, and if we've done things correctly, 6 should go back to itself. Well, you have 6 going to 5, and then 5 going right back to 6, and so we have exactly what we were expecting, 6 going back to itself. So our final function composition is just 1, 3, 5. Okay, so we've seen how this symmetric group works in terms of writing the cycles and then also doing this composition of functions essentially. And you can go back to the maps if need be, but it's just a shorthand notation that lets us work with the cycles in SN.